Hi, grade 9s, and welcome to 7.5, which is Reflections and Line Symmetry. So basically a line of symmetry is just a way that you can divide a shape and or two shapes, and there's a reflection, which means basically the same shape in reverse on the other side of the line. Now it can be sort of back to back, or there can be a space between them, but the important thing is that the points all correspond to each other, or certain points correspond to each other, and the reflection should be the exact same size and shape, just in reverse. So if we look at this polygon ABCD, we can draw a red line right through the middle of A, and then make another point at the bottom called G. Excuse me. And what this has done is this actually separates the bigger polygon into two smaller polygons that are both the same size and that are a reflection of each other. So for instance, this point B over here corresponds with the point E over here, and they both have to be the exact same distance from the line. Okay? And these lines that join B to A and join E to A, they have to be the same length as do the lines BC and CG with ED and DG. So all the line lengths have to be the same, and the shape has to be the same, just kind of in reverse on the other line of symmetry. It's often called the line of reflection as well. So point B relates to point E. Point A is shared. Okay, so it's basically just the same point for both of them. Point G is also shared by the two shapes, and then point C and point D are also corresponding. So this last little part here, BF equals FE, all that's saying is that this line here is the exact same length as that line, meaning those 2 points are the exact same distance from the line of symmetry. So if we've got an original shape here, and then we draw a line of symmetry that connects to the very bottom of it, and then do a reflection, okay, what we do is we basically take this shape and then fold it, so sort of fold it over the line of symmetry, and that's how we get our reflection, which means that this point right here is similar, or sorry, corresponds, it's also similar, corresponds to the other one. So you can imagine if this was a piece of paper that was shaped like this larger shape, and you folded it directly in half, this point at the top would go perfectly over top of this point in the bottom. And in the same sort of idea, these 2 points are corresponding, and this point and this point are corresponding, and this point and this point are corresponding. So they're all the same distance from the line. Blue and blue, green and green, red, red, and black and black. You can't just copy this shape on the top down, because if you copied this shape on the top down, you would end up with something like this. Okay, that's terribly drawn, but I think you get the idea, where the points don't match up because this point here is supposed to correspond with this point here, and this point here is supposed to correspond with this point here, and nothing matches up, and nothing's the same distance away from where the line of symmetry should be, which is at the bottom. So that's why it's very important that you understand that this is a reflection across the line, as opposed to just sort of copy and paste the object down. These are called tessellations. They're just basically repeated shapes. If we identify lines of symmetry, we can draw lines, but the lines have to be very specific. The lines have to divide these objects into 2 perfect halves, so that one side looks exactly the same as the other, just in reverse. So let's just get a different color here. All right, so let's look at the first object here. What happens if I draw a line that divides right down the middle? The question you've got to ask yourself, I'm just going to change the color of it. The question you have to ask yourself is what we see on the left side of the object the same as what we see on the right side of the object? Does this point here correspond to this point here? And when we say correspond, what we're asking is that distance there the exact same as that distance there? And it looks to be. I mean, we're just kind of eyeballing this right now. So if I refer to this line as, let's just call this line 1, we can say that line 1 creates, or line 1 is a line of symmetry or a line of reflection, because everything that's on the left side, if it was folded over, would match up perfectly on the right side. And you can see this with all these points. You know, I can take this point right here at the very end and compare it to that point, okay? And this distance right here is the same as that distance right there, just like the distance here was the same as that distance there. And that has to be true for every single point and every single line on your drawings. So that's one way that we could separate this drawing into sort of two halves, two reflected halves, using line 1 as a line of symmetry. Now I'm just going to use a counter example here using a different color line. So I'm going to use like a purple color line or a green color. Nope, we already got green on our chart here. I'll use purple. So I'm going to use a purple color line, and then I'm going to try and draw one through the middle going this way. Trouble with my colors, obviously. And we're going to make a decision as to whether or not this line, I guess we'll just leave it black, does this line represent a line of reflection, also known as a line of symmetry. So I'm just going to get rid of that, get my pen back, black. So this would be line 2. So line 2 separates the object vertically, right? The line of symmetry, we're comparing the top and the bottom now. And if we compare the top and the bottom, are all the points on the graph equidistant and reflected from bottom to top? Now, some of the points might be equidistant, so let's look at this point and this point. It looks like they're about the same distance away from that line, but the reality is if we fold this shape over, okay, this line right here is going to look like this on the other side of the object, which obviously doesn't match up. Because remember, we're not just copying and pasting from top to bottom or from bottom to top. What we're doing is we're folding it over the line. So all of these lines that are pointing from, down in the right to up in the left, all of those lines, when you fold them over, are actually going to be going the other way. So they're going to look like this, which means that lots of our points aren't going to be equidistant from the black line, and they're going to be actually angling in a different direction. So you can't always just use the distance between points. The shape that the lines make also has to be a reflection. So in this case, line 1 is a line of symmetry. There's two ends in symmetry, isn't there? Is a line of symmetry, but line 2 is not a line of symmetry. So there's an example and there's a counter example there. So let's go look at the next one across. So we'll draw a line in red again, and we'll draw that line right through the middle that way. And then we'll draw another line right here. And then we'll draw another line here. And we'll draw another line. Right here. Okay, now I'm just going to straighten out a couple of those lines. Make sure that I've got the right angle. This one looks pretty good, I think. Move this one up just a touch. Okay, so what I tried to do is I tried to split this object in half a bunch of different ways. And what we have to determine is, are these points going to join up? Are they corresponding for each of those lines? So how many of those lines that I drew are actually lines of symmetry? So if I look at the red line first, the one that's right in the middle, if I fold this point over here, is it going to match up with that point here? And is the line down from that point going to be still vertical when we flip it over? And it clearly it is. So that's kind of a check mark right there for that one. Let's look at the purple line. that's up here. Now we've got this thing diagonally sliced. And the question is, if I fold this whole triangle here over, is it going to match up with the triangle on the other side? So is this point here, sorry, I'm folding this way, is this point here going to match up with this point here, which we also used for the yellow, or for the red rather? And the answer is yes. If I fold this triangle over, that point is going to land on that point. And, you know, this point here is going to fold over and land on that point, okay? This line is still going to be vertical on both sides, and this line is still horizontal on both sides, so that's a reflection too. And you're going to find that when you go through all of these, so that was this line right there, you're going to find that if you go through all of these points, they all reflect perfectly from one side to the other. So this orange is the other diagonal, which means basically I'm asking if any of the points on this side of the orange line, do they line up with the other side if we folded it over? If I folded this over this way, would that point end up there? Yes, it would. Is this horizontal line, okay, right here, we fold it over, is it going to line up with this one? Sure it is. Everything's going to line up exactly the way that it should, which means that although the first item here, A, only had one line of symmetry, and I could have drawn a bunch of different lines on A, but I wouldn't be able to match it up with a reflection anywhere except from where I did it from left to right. However, on this B object, there's lots of different ways that I can fold this object across a line of symmetry and have it match up perfectly with the other side and have points that are perfectly equidistant from the line of symmetry. So basically, the mental picture you have to go with on these is, can I fold it over that line, and will all the points match up, and will all the lines be pointing in the right direction? And if that's true, then all of them are lines of symmetry. So in this case, all of the lines are lines of symmetry. So some objects are going to have one line of symmetry or no lines of symmetry, and other objects are going to have many lines of symmetry. Now, it doesn't mean that all lines are a line of symmetry. For instance, if I won't actually draw it, but if I were to put, well, maybe I will actually draw it. If I were to put a line right here on this object, that black line is not a line of symmetry, because if I take this point down here in the corner and I fold it over the line, it's going to end up here somewhere, which clearly isn't part of the object that's left on the other side of that line. So not every line for every object, even if there's lots of lines of symmetry in the object, like there is for this one, that doesn't mean that every line you draw on it is going to be a line of symmetry. It just means that it's got more lines of symmetry than, say, an object like this. So far, I've drawn line of symmetry through objects, but it doesn't always have to be that way. Lines of symmetry can be outside of objects as long as the reflected shape is still still works with the that folding method. So if we look at these four triangles here, let's look at A, B, C, and D, and let's count the red triangle as sort of the original shape. And what we want to do is we want to determine which of these are actually reflections of that red triangle and which of them are not. So what we have to do is we have to be able to draw a line that acts as a line of reflection. So we've got to test it out, basically. This green line here does this point, for the green line, does this point here, okay, if I fold it over, will it line up perfectly with the red? Sure it will. Will this point and this point? Yes, they will, because they're shared. That's actually where the fold is. And will this point, if it's, obviously if it matches on the other side, it's the same distance from the line. Okay? And it's still, this line here is still going to be a vertical line when it folds over. And this line here is going to match up with that line there when it folds over. Okay, so that we can say B is symmetrical, is a symmetrical triangle. I shouldn't say symmetrical, I should say is related by symmetry. So triangle B is related to triangle well, what's the red triangle, I guess. Can't even call it. To the red triangle. By symmetry. And what we're essentially saying there is line 1 is a line of symmetry. All right, let's test another line. Let's see if we can make some more of these triangles work out. So I'm going to do a different color line here. Maybe I'll do orange now. Is there any way that I can reflect the red triangle across a line so that it lines up with A? Well, it has to be a line that's halfway between A and the red triangle. So the only place we can do that is right here, more or less. Move it over just a touch. So that for that orange triangle, we have to ask ourselves the same questions. Okay? Does this point, and this is the first example where we've seen, that the line of symmetry is not touching the two triangles. For instance, this green line that we drew is touching both of the triangles. This orange line is not touching the red, and it's not touching the A, but it is the same distance away. So that distance there is same as that distance there. So it's got a chance to be symmetrical. Now we've just got to kind of visualize what will happen when we fold it over. So if we take this and then we fold it all the way over the line, will it line up here? And it will, because look, there's 1, 2, 3 jumps to the line, and 1, 2, 3 jumps to the line, which means at this point we'll hit that point. Is this back line here going to be vertical when you fold it over? Yeah, it's going to line up perfectly. It's going to be right there. And because we already said that this distance was the same at the bottom here, we know that this point is going to line up with there, which means that this bottom line is also going to line up with there. So we can say that A, the same thing, is related. Related. Nice spelling. Is related to red, and then I'll just put symmetry, so I don't want to have to type that whole thing out again. So we did find that our orange line is also a line of symmetry. Okay, so we can add that to the group here, line 2, and then, I don't know if you've seen those marks before, just like double quotes, that means exactly the same as what you see above. So we were able to prove that both B and A are symmetrically related to the red triangle. So let's see if we can do anything for C or D. Let's get the line tool back. Get the color. Put purple. Is there a place where I can draw a purple line that's halfway between the red triangle and C, where I can match up all the points? Well, the only place I can draw that is halfway, that I could draw a line that's exactly halfway between them, I got my line tool here, is right there, because I would say that that's halfway between triangle C and the red triangle. Just try and nudge it up a little bit here. Which means that this point at the top of the red triangle, right here, that point right there, get black pen, sorry. This point right here is the same distance away from that black line as this point. However, this does not necessarily make a reflection. This doesn't make a reflection. Because if we fold up point B, it is 1, 2.5, it is 1, 2.5, it will indeed hit point the top of point C there, and that works just fine. But if we look at the shape of the triangles, okay, the hypotenuse on C, that's the longer line, is angled down and to, well, if you just start at the top left, it's angled down and to the right. And the exact same thing is true on B. It starts at the top left and angles down to the bottom right. What that means is if we rotate this, reflect this, not rotate it, if we reflect this triangle from the bottom to the top, The problem point is going to be right here, because this point is going to go is 1, 2.5 away from the line. So it's 1, 2.5. So I have to count the same thing going up. So I go 1, half, 1.5, 2.5, and that places that point right here, which is clearly not part of the C drawing. So even though I could reflect this point here, and it would go 2.5, so it would end up there, and I could reflect this point here, and it would end up there. The problem is when I try to reflect this point up, it ends up here, which means our triangle actually has this shape, which clearly doesn't match up with C. So C is not related. Remember, it's not just one point that has to match up, it's all the points have to be reflected. So even if you can find just one that's out, in this case, it was this point up here was out, then we know it is not, and I just put that X in there to show that it is not a point on that is not a point on triangle C, which means we proved that it is not symmetrical. So line 3 is not a line of symmetry. And that was the only way that we could compare the red triangle to C. There's no other place where I could draw this line where it's perfectly equidistant. I mean, I could try, I guess, going a diagonal, but it still wouldn't match up. They're either symmetrical or they're not. There's no in between. So because we proved it with that third line there, we can say unequivocally that triangle C is not related to the red triangle by symmetry. But we've got one more we got to check. We've got to check D. Now, it looks like D might not be because it's kind of a long distance away and it's oriented in a different fashion, but that actually works in its favor, because if it's kind of copied and pasted like the red triangle is to C, like it's basically just like we took a copy and then put it above the line. If it's a direct copy of what's on the other side of the line of symmetry, it's probably not symmetrical, right? Because the direction of the lines has to change to get across that fold. So if I take a line, and what line haven't I used here yet? I've used green. I guess I'll use purple. Hopefully it doesn't look like it's black. If I find a point that I believe is exactly halfway between these two, and I draw a line, let's see what we end up with. And I believe this is going to be kind of tough because I got stuff all over the place here. From that point to that point, midpoint's going to be right about. Okay, this is going to be just kind of a hope that I got it right. Let's see, the point here. So this point is 1.5, and this point is 1.5. Okay, I think I got it. So let's look at that purple line right now. So this would be line 4, the purple line. Now we've got lots of shapes and colors on our red triangle right now, but we had to test it against 4 others, so that's why there's so much stuff. All right, let's have a look. Now there's quite a distance away from the line of symmetry on this one, but that doesn't mean it's not symmetrical. If I take this point, any of the points in the triangle, let's just start with this far one here. Okay, so I'm going to start with this point here, and I'm going to try and draw a line that is 90 degrees to this. Now, you don't have to do this. I'm just using this to try and kind of line myself up. And once again, I did a terrible job of that. So, sorry, I'm just going to try and draw a quick line that goes from. Now, clearly, that black line there can't be a line of symmetry because it's actually cutting the object in half. And so it's not intended to be a line of symmetry. I just want to be able to kind of line things up for when I'm checking. So I'm just going to make this like a dotted line or something. Now what I want to check is how far away is this point from the line of symmetry, and we'll compare that to this point. So if I look at the line of symmetry, I've got sort of 1 diagonal, 2 diagonals, and then kind of a half diagonal. So I would say that purple line I just drew there, was, you know, kind of 2.5 units, let's say. So this is 1 all the way across the box, like diagonally, 2 all the way across the box, and 2.5. So I'd say that the purple line, this point here, is exactly as far away from the line, the diagonal line, as this point here. So that one kind of checks out. That one checks out nicely. Now let's look at the same thing right here. Do those points, are they about the same distance away? So this one would be, you know, that's a unit right there, and we'll say that's half a unit, and then look at the other way, and that's a full unit, and that's half a unit. So I'd say this point checks out nicely as well, and you're going to find that this point checks out too. So if we were to take a piece of paper, and there's the fold line, and this triangle was drawn here away from the fold line, and then folded all the way over to the other side, all of these points would match up perfectly with triangle D, and this line here would still be there, and this line here, okay, this line here would end up perfectly there, and this line here would end up perfectly there. So the fold on this one is actually going to work perfectly, which means D is related. Even though it's the one that's the furthest away from the original red one, we were still able to draw a line. My line's not perfect, but we were still able to draw a line, that purple line, that when used as a fold line, reflected the red triangle perfectly. So is a line of symmetry. This is one of those units where, you know, some people are just better than others at visualizing the fold. And I must admit that I'm not the best at this, but I've become much better at it over the years through teaching this class, and also mostly through teaching drafting. So if you're really good at taking objects and shapes and sort of manipulating them in your mind, spinning them, folding them, reflecting them, you might want to consider taking drafting in grade 10, 11, and 12, just to give it a try, see if you like it. Because people who are good at that sort of thing, visualizing and able to turn objects around in their mind, tend to be very good at drafting and also tend to enjoy it. So that's just a little aside about drafting. Okay, so now it's going to get us to do some actual reflections here. So let's see what we got. I got some lines. We need to draw a reflection in the horizontal line through 2. Okay, well, there's only one way to draw a horizontal line through to y equals 2. It said y equals 2, didn't it? Through the horizontal line. Well, it has to be, because it's, you know, a horizontal line through here would actually just be the axis. So even though that's maybe not as specific as it should be, that's what it meant. Okay, so let's draw a reflection in the horizontal line through 2. Oh, it does say on the y-axis. Okay, perfect. Well, that's through 2 on the y-axis. That's where we need to be. So what we need to make sure of when we're drawing this object, and I'm going to draw it in red, is our reflection for each point has to be exactly the same distance from the line of symmetry. So if B is 1, 2 jumps, then it has to be reflected over here, and I'm just going to call it B prime. So C, exact same thing. C has to be 1, 2 jumps, so it's got to be 1, 2, and it ends up right there. I'll call that C prime. And A is shared because there's basically no distance between the point A and the line of symmetry, which means it just stays there. So it's both A and A prime, but we wouldn't call it A prime, we just call it A. So what does the final shape actually look like when we connect this up? Okay, so our symmetrical shape, and I'm just trying to do my best to freehand it, but I should be using a ruler. So there is our reflection. There is our reflection of the ABCD polygon about the line of symmetry, which is y equals 2. So it says, write the coordinates of the larger shape formed by ABCD, and its image, and then describe the shape and its symmetry. So when it says the coordinates of the larger shape formed by ABCD, what it really means is both shapes, I think. But what I'm gonna do, just to make sure that we're perfectly clear, I'm gonna put the coordinates of every shape I see on there. So here's the original. Okay, so the point A is at, got to start at the origin, right? So it's x2, y2, so it would be 2, 2. Okay, the point B is over 4 and up 4, so B is 4, 4. C, okay, C is over 6 and up 4, so that's x6, y4. D, okay, point D is over 6 up 2, so that's x equals 6, y equals 2. Now we're getting to the new points, right? So point, let's say point B prime, I'll just line it up with point B over here. Point B prime is over 2, or sorry, over 4, and on the x-axis, so that would be 4, 0. And then C prime is also on the x-axis. It is over 6, but it doesn't go up, so it's at y equals 0. So 6, 0. And I think that takes care of all the points because they share point A and they share point D. So those are all of the coordinates for every single point in here. And if you wanted to just do the bigger shape, you know, I guess it would be A, B, C, C prime, B prime, which we've got, but we also included D in there, even though D was only the halfway point. Okay, now what's the shape and the symmetry? So if we describe the shape, well, it's a reflection, you know, it's a reflected polygon. Polygon. So it's a reflected polygon. Actually, I should say something different here. It is, although it is a polygon, I could be more specific than that. So the resulting shape is a, let's draw the whole thing. If we look at this and say we took 1/2 and reflected it to make a larger object, well, that's a 1, 2, 3, 4, 5-sided object, which means it's a pentagon. Okay, so a pentagon means penta means 5, so it's a reflected pentagon with line of symmetry at y equals 2. And what sort of symmetry do we have here? Well, it's a vertical symmetry because we are projecting up or down, so it would be like a vertical symmetry. When I'm describing the shape, I kind of did both. I described the entire shape, but then I also said that there was a line of symmetry that basically helped us make the bigger shape. So if we're describing the shape and symmetry, I think maybe this is a little bit vague because what are we describing? Are we describing the big shape, or are we just describing just the little part there that we reflected? So you know what? I might just make a little note there. It's the big shape is the pentagon. The reflected part is a how many? 1, 2, 3, 4 is a quadrilateral. So it's a quadrilateral. Don't worry about that word. It just means quadrilateral. Just means 4 sides. And what are the points? The points would be A, B prime, C prime, and D. So just because the shape up here is a little bit vague, are we talking about the big shape? Well, if we are, it's a pentagon. That's A, B, C, C prime, B prime. And if we're just talking about the reflected part, the new part that we drew, then that would be a quadrilateral because there's only 4 sides. 1, 2, 3, 4. And the points are A, B prime, C prime, and then D. A reflection in the vertical line through 6 on the x-axis. Okay, so we're still drawing a reflection. We're just doing it with a different line. So if we draw a vertical line through 6, that's from there to there. So that would be a vertical line through 6. Now let's just look at where our points would end up. So I don't have enough room to draw the points, but we'll kind of take a guess here. So if we're drawing it through the vertical line through 6 on the x-axis, our points are going to be over here on the right side. Excuse me, I got to sneeze. And make sure I didn't sneeze into the microphone. So let's look at the points. Okay, we've got point B right here. Point B is 2 hops away from the line. So 1, 2 hops of the line away. That would be B prime right there. Okay, point C is the same. It's still right on the line. Point D is the same. It's right on the line. Point A is 1, 2, 3, 4 hops. So I got to go 1, 2, and again, I'm just going to have to estimate this. 3, 4 would end up somewhere right about there, and that would be A prime. And those are the only points we need to draw because it shares C and D. So the final thing I have to do is I just got to join these guys up. And if you visualize folding this piece of paper from this side, folding it over the line, you're going to notice B does line up with B prime, A does line up with A prime. If you ever have any trouble visualizing this, you can absolutely take a piece of scrap paper, draw out one of your shapes, and then just fold it where that symmetry line would be and see, because you can, the paper's see-through, right? So you can see if your dots for your corners line up with the dots on the other side, or if the lines are pointing the right way or whatnot. So even if you have trouble visualizing this, you can use paper as a manipulative to double check. So a reflection in the vertical through A6 on the x-axis would look like that. A reflection in an oblique line, oblique just means an angled line. Okay? There's horizontal lines, vertical lines, and oblique lines, and I think we did that in Unit 4, maybe. A reflection in an oblique line through 0, 0, and 6, negative 6. Okay, so let's find those first. 0, 0 is the origin, and 6. So I had a look at this, and I looked at it for a while, and I thought, this question's way too hard for grade 9. This is sort of something I would do in like grade 10 drafting. And then I realized, yeah, there's probably a mistake in it. So let's go back up here and see where this says 6, negative 6. I think that's a mistake. I think it was supposed to be 6, 6. I'll change it for next year. If it was 6, negative 6, we could go over 6 and down here somewhere for negative 6. You could still reflect this object down there, but it's really difficult because just the way the shape is oriented to this line would make it very, very difficult. Doable, but not something we would do in grade 9. So make sure you scratch that out and put 6. Put 6 and 6 instead of 6 and negative 6. So what we're asking here is we start at the origin, 0, 0, and then we go over 6 and up 6, and we end up with a point there, which makes a lot more sense because our line of symmetry is touching the object. It doesn't need to touch the object, but it makes it easier when it does. So there's our line of symmetry right there. Now, the reflected object on this one's going to look a bit strange, and it's going to look a bit strange just because of the odd shape of this quadrilateral and the way it's lined up. So what we need to do is we need to reflect and pretend that we are folding diagonally this time, which means that this point D is not going to go straight horizontal or straight vertical. It's going to go across and sort of up and toward the corner. So let's look at how far away this point D is from the line. And we know that point D is going to end up over here somewhere. Instead of measuring straight in a 90-degree line straight in a 90-degree perpendicular to the black line, we can do it a different way, which probably is a little easier with the graph paper. As long as we can convince ourselves what the angle of this line is when we fold it over, we can count much easier. So if we know that we fold this over and you can visualize that line will go from horizontal to vertical, then it makes it a lot easier because you can just start here, and I'll just do it with red. So if we're going to do this point here, you can start here, and instead of trying to skip to the line across, diagonally across these boxes, let's just use the regular boxes. So that's 1, 2, 3, 4 to point A. So point A to D has to be 4. And now, because we're going across a diagonal, we know that has to go up this way at the same amount. So it's going to be 1, 2, 3, 4, and our point D prime, so that's the new one, D prime, is going to end up right there. And you can just kind of eyeball it at this point. You're like, does that look like it's the same amount? Sure it does, right? I mean, you can even see it. It's 1 diagonal, 2 diagonal, 1 diagonal, 2 diagonal. So it's a different way of getting to the same point. And we do the same thing with C, because C is a horizontal line, just like D was. C is a horizontal, and when a horizontal folds across a perfect diagonal, it goes vertical. So same thing with C. We got 1 jump, 2 jumps. So we got to do 1 jump, 2 jumps to get up to there, and that is C prime. And as always, you just got to join it up, and make sure when you're joining it up that you join it up by the letters, right? So A, D. So if A connects to D, A has to connect to D prime as well. So there's D prime up there. And then B has to connect with C, so B has to connect with C prime. Okay. and then D and C line up on the original, so C prime and D prime have to connect on the original. And then you end up with a shape that looks like this. Now this is the first one we've done across a diagonal line of symmetry, and it doesn't really even look like it's the same object, but clearly it is. I mean, you've got all these points the same distance away from the line. It's just that you're folding it diagonally instead of folding it vertically or horizontally. So this point does indeed go up there. It is the exact same shape. All the lines are the exact same length as the corresponding lines. But because it's folding across a diagonal, it just looks a little bit different than some of the ones that we did up here, which look, more traditionally mirrored objects. Now that should be enough information to get you started. I would definitely recommend that you use graph paper for this. And if you don't have graph paper at home, I put some pictures at the top of the unit that are printable graph paper that you can just print off. And if you want, you got a ruler and a pencil, you can just draw one of these little grids as well. But it is so much easier to do if you have graph paper, or if you're able to create some quick little graph sections. It makes the work so much neater and so much nicer. Okay, best of luck with 7.5, and yeah, we're getting near the end. I think just 7.6 and 7.7 in the next couple days. As always, if you've got any questions, just give us an email and we'll do our best to help you out.